This is my Physics 2 Lab 3 report, Magnetic Field of a Bar Magnet. The introduction and basis for it. The purpose is to measure the distance dependence of the magnetic field due to a small bar magnet and compare to the distance dependence predicted by the equations for the on and off axis magnetic fields derived from the Biot-Savart law. Models and fundamental principles, that law, and measuring the magnetic field, and then these laws given in the instructions. The procedure summarized is basically just measuring magnitudes of a magnetic field using the phone, the magnetometer on a phone, and sliding it in various directions on a meter stick, so that you can measure where it is when you hit the right spot. The system is the magnet, and the phone and Earth are in the surroundings affected by the magnet. This is the data recorded and some of the calculations. So all of the data recorded is in the spreadsheet, and the spreadsheet makes the graph of the natural log of B versus natural log of R. And the line of best fit of that is the approximate in, which is basically how the radius or distance is related to B, and the y-intercept is natural log of k, so we found k by doing e to the power of that value, which got us 9.8463 times 10 to the negative 7th. And then using that, we can plug that into this equation for the dipole moment, k over 2 mu naught over pi, and we get 1.2308. This is all the coding. So the top right box is plugging in our mu mag and making the r mag and r hat the correct values, as well as the b, to make sure they all fit the equations. And then below that is the observation points of a distance that we plugged in that distance away. And then on the left is all of the observation points made in order. So it's all the arrows drawn correctly. And then the bottom right is calculating d-perp distance and the observation location for that, and the observation approximated value that it should be according to Biot-Savart law. This is the computational model. This is the picture that we got. So the orange are on the parallel axis, and they're twice as big as all the blues that are in the perpendicular axis, which is right according to the law. And all the values are below it, saying which direction they're in, and then B at 45 degrees at a distance D is at the bottom, and our measured B was about 0.5 times 10 to the negative 5th off, so about 40% error, or 25% error. So pretty close, but not quite, which could be due to several errors in the experiment calculations, which we'll go over in a second. The what if and why. What if we hadn't oriented our experiment with magnetic north and had just laid it out? Basically, if we hadn't accounted for the magnetic field of the Earth, the magnetic fields would have intersected and either would have canceled out in a certain way that we wouldn't have been able to measure because we wouldn't have known what it was, and the results would just be inaccurate because we wouldn't know how much the Earth magnetic field was affecting it. And if we doubled the magnet, basically by adding another magnet, the magnetic field would either be doubled or it would be completely canceled out, depending on if it was north to north or north to south. The conclusion, the possible errors could have been from slightly misaligning from north and the inaccuracy of the phone readings due to all the interference from other magnets in the room and just being near other metals and technology and things. This means that distance dependence is very strong for a magnetic field, and the farther you are, the weaker it is by like a factor of 2 or 3. And it supported the purpose because it proved that the distance dependence of the magnetic field was very strong.